Okay, good afternoon, everybody, or good evening, should I say. Today, I would like to do a short stream, and it's about 3D printing and medicine. So, it will be just going to be a quick stream, probably around 10 to 15 minutes or so, although possibilities exist if you guys are asking about something you might it will be longer it will go longer than this. Wait, okay, now let's go. So uh, have any of have any of you ever heard about the term 3D printing or 3D printer or something like that? Today we will be discussing about the fundamental aspects of 3D printing and what is it actually. If you want to make something, create something, typically there are two ways. First, you put it into a you you power a material into a cast, into a template or a cast. So it is called casting. In the left image, we can see that gold or bronze is being in liquid form is being poured into a cast, and then after it cools down, it will solidify. This and a more familiar approach here is also used in the kitchen. For example, if you have jelly or pudding, you first heat up the mixture. You first make the mixture and then you heat it up, and then you pour it into a template or a cup based on the shape you want. It can be, for example, oops, it can be heart shaped, for example, or it can be cubical, or any other shapes. Okay. The second approach, you would go from something that is already created, and then you reduce it into the shape you want, and this is called, for example, here in the left image, it's sculpting. You start from a cube, for example, or a block of wood, and then you reduce it little by little to make an art figure. And then you can also use like Play-Doh, or I don't know what's the generic name, because it's a trademark name. I don't know. Plasticine, I think. Yeah. Yeah. If you have played with plasticine as kids, I think that also counts as how you create objects. And then comes the new technique. It's called 3D printing. The difference between the 3D printing and the methods that we have just discussed now is that in 3D printing, you make the object from zero. Make from zero, the build plate, we will explain about build plates later. From zero object into something, into an object, into a 3D object. how can it be done? It is done in a layer by layer basis. So it first builds like you first build this stack of material, and then you move up one ladder, and so on until the desired object has been created. Layer by layer, the layers are very thin. About in a conventional 3D printer, it would be about 0.2 millimeters. Yeah, 0.2 millimeters each layer. So we are making object from 0 to something, not from something to 0, as in sculpting. And then the second is that we do not require physical templates or physical templates as we will use in casting. 3D printing was invented by Chuck Hull in 1983. The first type of printer is called stereolithography, or SLA. What kind of disciplines are involved in 3D printing? We can see here there are mechanical engineering, and then material science, chemical engineering, and computer science. Why computer science? Because computer science is required to control how the 3D printer works. If you cannot control how it works, it will not be able to deposit materials properly. And behind all this, we have to remember that 3D printing is a form of art. So there is some artistic element involved, not just the science only. What can you print with 3D printing? If you have an object, that anything that has a 3D shape, be it a water bottle or be it bolts and screws, or maybe forceps or whatever that you can print. Even 2D patterns can be printed if you extrude them. For example, you want to make your name. For example, John. You can extrude it so that it has some 3D shape beneath, some depth. And then you can print it. As long as we have the digital template or the 3D model, as we will affectionately call it, you can print, you can make it, you can fabricate it with 3D printer. And what are the types of 3D printer available in the market? There are many types. There are the FDM, the SLA, the SLS, and also some 3D printers can also print metals. And there is also an inkjet 3D printer. But our focus today would be the FDM, and the SLA printers. What is FDM and what is SLA? We will explore in depth. But first of all, FDM refers to fused deposition modeling. Or so you deposit something layer by layer, in a layer by layer manner, I mean, from 0 to something. So we can look at this here. the parts or the anatomy of a 3D printer. First of all, you have the frame or the skeleton of the printer, and then you have the power supply. And here we see there is a build plate, the location or the place where the object is going to be printed on the first layer. And then you have the motors, the X motor, the Z motor, and the Y motor. How does it work? First of all, here we can see the extruder. The extruder is the element that heats up the material or the thread here called a filament. It can be PLA or ABS, or we will be explaining about it later. But the extruder here, it heats up the filament that goes through the filament drive all the way down to the extruder until a specific temperature is reached. In the case of PLA, it will usually be 200 degrees Celsius. And then it melts, and it will drop down on the appropriate coordinates of X and Y. After everything in the first layer has been achieved, the Z motor will increase a little by 0.2 millimeters, and then it will move to the second layer. So we can see here in this anatomy, the filament spool is here, where the filament is stored, and then the filament goes all the way down through here. The drive motor, or also called the extruder motor, will control how long filament will be going into the extruder or the hot end. The hot end then melts filament to the appropriate temperature, as we have explained just now, and then it extrudes the material. After it touches the build plate or the previous layer, it will gradually cool down, and it will become solid. Here we can see a 3D printer. In fact, this is mine in action. We can see that the X and Y motor are moving, and then it deposits material according to the program pattern. My 3D printer is Ender 3 Pro, which was bought on late 2020. It costed me around $215 US. And now I have upgraded it so that it has a direct drive filament feeding. After we have understood how it works, and now we would like to move to how we print a 3D model. First of all, you must have a design. You must have a 3D model by designing it, or either also by extracting it. You can extract models from many sources, and for medical models, it will usually be extracted from medical imaging files rather than being designed de novo. After you make the model, you would like to export it into a format that the 3D printing software or the slicer software would understand. The format is usually .stl. Why? It's called stereolithography, or the first kind of 3D printing that we have mentioned before. But it also works with other 3D printing mechanisms. After you make the .stl file, you want to slice it. What does slicing mean? It means to tell the computer how should the 3D printer behave, how it moves in each coordinate, and how much ink or how much filament it is going to extrude. The file is called .g code. After you have the .g code file, you move it into a memory card, for example, the micro SD, and then you insert that card into the 3D printer, and then you print it. The printing process can take anywhere from minutes to even days. And then after your 3D printed model has completed, sometimes you would like to do post-processing. For example, to remove supporting materials, or if you want to make the model smoother. And then we have the choice of materials. For FDM printer, it is usually a thermoplastic material. It means the material is solid, and then you can melt it when it reaches a certain temperature, during which it will be extruded and formed into a model. But after it cools down, it will solidify again. So most of the thermoplastic materials used in FDM is recyclable. For example, the PLA, polylactic acid. Polylactic acid is a kind of non-toxic, and it is also biocompatible. If you have participated in, if you are a healthcare worker, you might be able to see suturing threads. If you want to stitch up wounds, and sometimes you will see the material is PLA. Yes, it is the same material that is used in this 3D printing, so it is biocompatible. And then comes the ABS. The ABS is also non-toxic, but it's less organic, if I'm not mistaken. And then we have the TPU, or thermoplastic polyurethane. It is a flexible material and requires more advanced technique to print compared to PLA or ABS. And then for stereolithography printers, you will need resin or a liquid material. The liquid material or the resin will be exposed to UV, and what happens next is that the exposure to UV or ultraviolet light will cross-link the polymers in the resin. What does cross-linking means? It means when you have, here are the strands of a polymer unconnected, but if you have a cross-linker, for example here, it will make bonds. And what does this mean? This means that it will solidify from the liquid resin into the solid. And what are these blue things, blue lines here? They are the cross-linking materials. The cross-linking material, it could be anywhere, but it is also provided in the resin. There are also some types of resin available: standard resin, tough resin, and flexible resin. We will talk about it later. And then what does this, we come to the second part of our talk. What does this have to do? What does 3D printing have to do with medicine and the biomedical world? We can see that if we can create objects from zero and also from medical imaging, it will be able to help a more personalized medicine or individualized medicine. What does it mean? If we recall that everybody is unique, nobody has the same set of fingerprint or the shape of ears, of both ears, and so does with the other shapes found within our body, our bones, and our joints primarily. And also soft tissues and other tissues, for example, the heart. It varies from individual to individual. So there are 4 levels of how to implement 3D printing in medicine. The lowest one that we can do with low-end printers or budget printers is creating organ models for pre-operative planning. And then if you have a little more expensive one, you can create implants. For example, if for the total hip replacement or total knee replacement. And then you also have bioactive and biodegradable scaffolds up one level. What is this? So what is a scaffold? A scaffold is a structure. For example, I exemplify with a cube. Here. Okay. So the scaffold is this object, this cube, if I call, and then you would like to implant it into a diseased area. For example, a bone is broken and the central part is shattered. So it's taken out during surgery. Taken out. So you only have the 2 ends. Typically, you would do like, during the surgery, you would like to put something to bridge the 2 so that regeneration occurs. But this usually this bridge thing is inert and regeneration doesn't occur. It only connects the 2 parts. But if we add some scaffold that has growth factors in it, we can trick the bone cells in both ends to migrate here and create a new bone along the path. Create a new bone along the path so that it will connect in the end. This is a scaffold, or scaffold is like tissue skeleton. You can analogize it, and then we have the most complicated 3D printing in medicine. It is called bioprinting or biofabrication, where we print cells or organs directly. Here is the example that I made, creating organ models. For example, this is the skull base, and then we see here the non-bioactive implants here. If we make an implant, there will usually be standard sizes and variants. So if the patient's anatomy does not match with the standard set of tools available, it will carry risks. For example, infection, and also maybe anatomical or cosmetic discomfort. But if you make a personalized knee replacement, it will look much nicer here and can carry much less risks of infection and anatomical issues. And then the third is the bioactive scaffold that we have just talked about. And then finally, we would like to be able to print organs or cells directly. If we can incorporate cells into an ink, and the live cells will be able to be printed during certain if certain conditions is satisfied. Where does it lead us to? It leads to a term, or tissue engineering and regenerative medicine. This is a continuum. So in the past, people only talk about tissue engineering, but now researchers are primarily using it for regenerative medicine. So this forms a continuum. So the two terms are usually combined. This is the interface between engineering and biomedical science. It is about how to make tissues regenerate after injury. This is the therefore term is the frontier of biomedical 3D printing. Here we can see some tissues in our body can regenerate easily. For example, if we have a cut in our skin, it will be able to close easily. Why? Because the cells, the cells of the skin, in this case the epithelium, it constantly divides. The lost cells are replaced easily, and then come a more stable tissue. For example, the liver tissue, which will divide if a damage is detected. And then this is where we would like to where we would like to implement tissue engineering and regenerative medicine in the permanent tissue, because these tissues, because these cells, once they die, they will not be able to be replaced, or we can say that the regenerative capability is very limited. For example, the nerve cells, and then the muscles of the heart, and also the muscles in the skeletal muscles. So skeletal muscles do not divide. They only undergo hypertrophy. If something happens to these tissues, it will not regenerate into a functional tissue, but it will become a scar. Okay, so this is the bioprinting. As we can see here, we incorporate live cells into a hydrogel or other medium, and then we print using that medium that contains cells. This is it for today, and I am planning to make more episodes for this 3D printing series. For example, in the next one should be about how to make a simple 3D model in Blender, and then how to export and slice a model in Cura, and then how to 3D print a model. This will be tentative, and then the physics and science of 3D printing, and troubleshooting common problems in 3D printing. Then finally, how to export and optimize 3D models in Cura. Let me see the comment sections. Okay, nobody's here. Thank you for watching. I will end this.